Welcome back to another episode of Through the Looking Glass. I'm your host, James Glassoff, joined once again by Richard, aka the Mad Hatter, our in-house AI nut. Quantization and floating point.
Yes.
Let's take a deep dive. Explain why it is mentioned so much when deciding large language models and the requirements thereof.
Cool. Okay, yeah. So at the end of the day, everything boils down to your CPU or GPU and how much memory each clock cycle can handle at a time, or how many, let's say, characters a GPU or a CPU can handle for every cycle. That defines effectively the length of the number. And the longer the number, the more accurate you can be. As in, the more numbers you can have, or the more characters in a number you can have, the more variations you can have, and therefore the more accurate you can be. So it all talks to variations and accuracy. So quantization is effectively the idea that when we have these models and we do the maths on the models and we generate these numbers that represent a word, for example, and that word has a relationship, the more, or rather the longer the number we can keep, the more different variations and different words we can keep, and therefore the more accurate we can be and the more specific we can be. So when you hear something like floating point 8 versus int 4, for example, what these are basically saying to us is the length of the number and therefore the accuracy of the word that we can store. Now remember, we're doing millions and millions and millions of numbers, and the quantity of those things then grow in sort of this exponential way. So if I have a word that is 3 characters long or 4 characters long, maybe in the int 4's example, or I have a word that can be 8 characters long. An 8 character long word isn't just double the amount of words and accuracy, it's an exponential amount more, it's an exponentially higher amount more words that we can store, and therefore differences we can maintain, and therefore accuracy we can have, because we have many more words in that dictionary discussion. In a similar way to the small pocket-sized dictionary and the big dictionary, the bigger the quantization, the more accurate you can be, the more processing it requires, and the bigger the model. So again, it also plays into that space of how large our models are and how do we fit them and where do we fit them.
So a higher floating point allows for more accuracy. Doesn't necessarily mean every parameter is going to be more accurate, but it allows for that accuracy.
That's correct, yes.
How does this affect sizing requirements, and how does this affect your calculation of your memory requirements?
So this is very important. Going back to the idea that this is exponential growth using bigger quantization values, is again, you can drop accuracy in your parameter. So your parameter count is how many words you keep. Your quantization is how big those words are. So in the combination of those things, you can manage those two variables: is how many words versus how many variations of words we can cater for in a model. That then defines what GPUs we need to look at, or what combination of GPUs. Sometimes you need to consolidate them or whatever. That's a whole different discussion for another day. The point is, those two principles are very important in sizing. So if you want high accuracy and you need a lot of words, so you want high accuracy in terms of differences of words, and you want a lot of words, you're obviously going to have a bigger model. And again, most of the let's call it the guys who make the publicly available LLMs, they typically run in 3 sort of sizes, like a small, medium, large kind of model, and they all roughly aim for the same kind of utilization of GPU memory on your GPU. And so oftentimes you are limited to the models you can use by the available memory you have, but you can choose models that maybe have higher or lower quantization versus higher or lower parameters. And you end up tuning and trying to find the right combo. And generally speaking, the little models that fit in that small space are just not quite accurate enough for, or not quite detailed and accurate enough for most business needs. So you want something at the very least in that sort of middle category that's going to fit in your sort of, let's say, 64 gig mark. Because there's one other thing people forget when they're sizing these things is your model takes up space, and you also need working space in your memory. So if you have a model that perfectly fits on your GPU, it's actually probably going to panic a whole bunch of the time because it's got nowhere to actually store its working memory. So that's what we call context, which is, again, another discussion for another day. But when you're sizing, parameter count and quantization are the two main things that define the size of the model. And then on top of that, you need some space for context, which is working memory.
So we're currently seeing crazy shortfalls in the supply of various components. We're talking memory, storage, compute, GPUs to a large extent as well. Do you think there will be a swing towards more efficient models with perhaps lower floating points, lower parameter counts that can still do the jobs to mitigate this shortage of componentry?
So it's an interesting one. And I think the componentry shortages, which is actually because of exactly what we're talking about. At the end of the day, that NAND flash, that's that little chip that goes into your memory, into your GPU, into your storage devices. All of those stuff is all that NAND that's being swallowed up by all the big AI guys because they need the space to run their models. But they're all hitting those ceilings rapidly. We all are seeing these massive cost increases because everything's gone up because there's no supply of this stuff. But what that is resulting in is people working on various mechanisms to optimize, exactly as you were asking, various mechanisms to optimize how the models work, how they are combined and consolidated. Because whilst we've been talking in a very sort of hopefully relatively simple way to kind of explain the principles of it, there's a lot more going on than just words and numbers. There are ways to compress the data. There's ways to optimize the utilization of the data. There's so many areas of optimization that people are driving towards to try and improve the capacity and effectively almost zip compress these models and make them run in smaller spaces. There's a lot of work toward that. But there is, at the moment, AI is a bit of a wild west. So every company is doing things in different ways. The standards, well, they're not really proper standards yet across the board. And that's a good thing because in the early days, you want people to discover and to create. However, what that means is a lot of these ideas and concepts are sort of kept behind closed doors. So not all brilliant approaches to make efficient, better, more accurate data are all in one place, used by one person to create this perfect model, this sort of utopian model that's brilliantly accurate but tiny and efficient. So it's at this point in time, it's just really nobody knows exactly where we're going with the sizing, but they know what we need to do, which is obviously to try and handle the fact that components and stuff are just so expensive. So we have to manage.
Well, whether it's accelerated production of the componentry required or more efficient models, let's just hope it gets figured out soon because I'm sure we all have some dancing cat videos we need to generate over lunch. Thank you.